So, well, welcome, colleagues. Very warm welcome to our second Science for the Green Economy series. Can I introduce myself? I'm Simon Pollard. I'm Head of Environmental Science and Technology at Cranfield University, and it's a great pleasure to welcome you to this event. It's held with our colleagues Herbert Smith Freehills and Julie Vaughan, who's our co-host. So, we're a small, select crowd, and what we would like to do this afternoon is demystify for you big data and environmental informatics. What I've learned is when you say the phrase big data, you either get a groan, or you get a wry smile, or you get a big smile and people roll their sleeves up. I think at Cranfield we're the big smile and roll your sleeves up brigade, but it does seem to divide opinion. And so hopefully this evening you'll be able to go away with a bit of understanding about what it can do, some of the pitfalls, some of the aspects about turning data, of course, into knowledge and real information of value. So the format for our evening's proceedings is three short vignettes from our colleagues from Cranfield and Herbert Smith. I'll introduce them in a moment. And then there's a Q&A. There's an open Q&A session. And then afterwards there'll be an opportunity for some networking and drinks. So let me introduce our colleagues speaking this evening. Dr. Steve Hallett, who's a Principal Research Fellow at Cranfield. Steve runs one of our national data sets at Cranfield, Landis, Land Information Systems. It's national capability, so it's unique to Cranfield. And he's going to introduce us to the generalities of big data and really try and bring this alive for us. Then we'll have Dr. Tim Farewell. Tim's a Durham-trained geologist, but we'll allow that to pass. And Tim is the custodian of the National Perils Directory, which is again a Cranfield unique data set used by the insurers and reinsurers in the city. And Tim's really going to then bring things to life on a particular case study around informatics. And then we've got David Cooning. David, thank you. He's a commercial lawyer in the technology practice at Herbert Smith, who's going to talk us through some of the legal and contractual issues around data and information. After our colleagues have spoken, Julie will manage the Q&A for us. So with that, Steve, can I ask you to give us your overview?
Thanks very much, Simon. Very good evening, everyone. First of all, thank you ever so much for coming along tonight. It's a pleasure to be here, and thank you to Herbert Smith for hosting this. As Simon says, my name is Stephen Hallett at Cranfield University. I'm a Principal Research Fellow in Environmental Informatics. One of the things that fascinates me, of course, is big data, and it's a great pleasure to talk to you about this tonight. It's something that's mentioned widely in the press. It's reported extensively. People talk about big data, and it is actually, of course, something that affects all of us as citizens, and it's also something that affects businesses. It's something that can't be ignored in a business context. But what actually is it? And in a few moments, I'd like to go through some thoughts about big data. And I'll first of all start off with a description of actually what is the data that's big. And the first thing to say then is that this data is coming from a variety of sources. Very large data sets from the public sector, from private sector, and from indeed the public. One of the things that's made a big difference to this whole field in the public sector has been the Open Data Initiative and this notion of the data.gov.uk portal that makes available huge amounts of publicly collected information for data scientists and anyone who has an interest in the electronic government. A rise of commercial data service providers, subscription data sets, extensive range of those, as we'll see as I progress. And of course, I cannot overstate the importance of the social media and the role of volunteered information from things like Facebook and blogs and so on. This data is coming from a variety of different sources, this big data. It's coming from social media posts, as I've mentioned here, but a whole load of other types of data like imagery, videos. Think of YouTube, the amount of videos posted all the time to YouTube, transactions, logs, the digital footprint of our lives as we live them, GPS coordinates, and increasingly important, the role of connected machine-to-machine interfaces, the sensors in physical hardware which are communicating electronically. What we can say is the rise of big data needs a construct to discuss it. And what I'd like to do is to pick up a concept, I think, put forward by Forrester consultants, and picked up by Gartner and many others, the 3 V's of big data. This notion of volume, velocity, and variety. And what I'd like to do is just give you some thoughts about each of these in turn as we go through the presentation. These V's, if you like, have necessitated new ways of dealing and handling with data in terms of its storage, its transformation, and how that data is actually then transported to the end user applications. Co-evolved with these novel storage and handling approaches are the analytics, the clever algorithms that can actually sift through these large data sets, looking for patterns and extracting sense from those, exploiting connections between them. It's definitely the case that the government strongly recognize the importance of big data and get behind it in a whole range of sectors. And in our field, the government have invested, for example, 90 million over the next 5 years to set up a range of centres for agricultural innovation as part of a much wider agri-tech strategy, just to give an example from our world. So big data is here to stay. It affects all of us. And really, we are both producers of big data and we are consumers. So I think the phrase would be the prosumers. We are prosumers of big data. It's a nice phrase. But there's a number of challenges, as we'll see. First of all, then, I need an analogy. So bear with me for a moment. Just imagine, for example, that 1 megabyte of data represents a square meter of land. So, you know, not a great deal of size, about that sort of area, 1 by 1 by 1. Meters round. Now we know how big that area is, if we go back in time to the year 1920, if we take all of the encoded information in the world that existed at the time in tabulated form, of course it would have been in reports and books and surveys and so on, if that was held in contemporary informatic solutions, according to Sanderson, it would have required an area of land, with this analogy, bear with me, somewhere in the region of the island of Madagascar. If we step forward in time to 2010, that landmass would have expanded to require the whole planet. Bear in mind, colleagues, that this is 4 years ago. 4 years ago, that's not very long. If we step forward in time to 2020, now we need 1,700 globes. This growth is exponential. It's quite phenomenal. We're dealing with very large data sets. The CEO of Google, Eric Schmidt, made a fantastic and fascinating inside comment recently. Every 2 days now, we create as much information as we did from the dawn of civilization until 2003. That's extraordinary. Something like 5 exabytes of data. That's 10 to the 18 bytes. I was looking for some other statistics and came across Cisco Systems Visual Networking Index, which gives a very fascinating projection of what might happen by 2017. I should just point out that, of course, many pundits talk about us moving from the industrial age to the information age, or shall we say the zettabyte age, or zettabyte age, or however you pronounce this. By the year 2017, annual global IP traffic will be somewhere in the region of 1.4 zettabytes per year traveling across the internet. Nearly half of all the traffic will come from non-PC devices. A big shift going on in terms of the hardware. The traffic from wireless and mobile devices will exceed the traffic from wired devices, say Cisco. And my favorite one, which is the gigabyte equivalent of every single movie ever made, will cross the global internet every 3 minutes. I find that staggering. And that the number of devices connected to IP networks will be 3 times as big as the global population. So we live in extraordinary times. It's definitely the case, though, that volume, the first of our V's, is a challenge in big data. So the increase in volume of data is causing enterprise systems, IT systems, great challenges dealing with growing and growing and growing traditional transaction-based data. But now these organizations, to retain competitive advantage, have to contend with a whole range of new different types of data to give the edge. They have to deal with IP-connected devices, social media posts, imagery, videos, GPS log files, and documents like doc files, HTML, click trails, and so on. So it's definitely the case that this growth in volume of data is a huge problem for storage, but as we'll see, it also presents a massive issue in its analysis. The BBC have actually released a number of interesting statistics. Did you know that the engine of a transatlantic jet aircraft flying from New York to London is generating 10 terabytes of data every 30 minutes? Now, at Cranfield University, the engineering colleagues there are working with Rolls-Royce on the sorts of sensors that are needed to work in these very hazardous, high-stressed environments. Google are receiving 2 million search requests every minute, and in that same minute, something like 100,000 tweets are being sent globally. I don't know about you, I'm not a great tweeter myself, but it's worth just dwelling on tweets a moment. There's a really interesting app which we've been playing with called Invisible Cities that looks at some of the major cities around the world. And so this is New York. And I've got a little video here that just shows you how this thing works. If I just try and run this. So what we see here is the peaks represent the volume of tweets that have been posted around the city of New York. And effectively, each of these tweets is time-coded. It has a time stamp of when it was sent. So you can roll back in time and you can see the range of tweets and where they are. Now, of course, we also know that the tweets contain content. And where many tweets are containing the same sort of keywords, we talk about trending, some things trend. And what you can do is pick up these trending words and look for the links between the different tweets. And then, of course, you can drill down and you can actually inspect each of these tweets that correspond with a particular with a trending word, you know, and you can actually identify what's going on. So here, of course, is somebody hoping for an adventure today, aren't we all? So, of course, we're interested in what you can do with tweets, and let me just give you an example of what my colleagues, Jason and Ian at the back, have been doing with tweets. We were concerned about the big freeze that we'll all remember at the beginning of 2013. And we were interested in the impact that this weather was having on people. And so we did a mine of the tweets out there and recorded something like 20,000 tweets that were mentioning keywords like snow or ice and freezing. And you can see up here where those are. And when we produced a choropleth map, linking those to municipal boundaries, it produces a map like this. And what that faithfully reproduces is a map of where people live in the country rather than where they're being affected. So the team also then produced a separate set of some 40,000 random tweets, which effectively gave us a blind test against that. And you can divide the two things through and then produce a normalized tweet of where the people are actually being affected by these events. And I think you'll agree it's very interesting to look at the map of the tweets and the patterns of where those are, and a satellite image of the country at the same time. The point here is that in addition to looking at the environmental conditions, the research is interested in where people are being affected by the environmental conditions. So the next V in the story is velocity, the velocity of data. When we talk about velocity, then, we're referring both to the speed at which data is being produced from sensors, and we're also interested in how fast that data is being handled, processed, and made available in applications to meet the demands of applications. Of course, when we talk about real-time data, typically we're talking about data coming from a range of sensors. And I've got a number of sensors here, just to give you an idea. This is a sensor here which is doing humidity and temperature, taking humidity and temperature readings. Here's another sensor which is a light meter. And on the end of this is a microprocessor, an Arduino microprocessor unit that you can plug these things into. This is an accelerometer that's giving us indications of the X, Y, and Z. One of these things that would be inside your hard disk if you drop it on the ground and turn it off. This is a Bluetooth module, which is used to communicate with your application. And of course this, very importantly, is a global positioning satellite module, very, very small. I think it would be very interesting just to know actually how many sensors are there in this room right now. I suspect the answer is hundreds. If you think about it, all our mobile phones have many of these sensors embedded in them. The role of dealing with these sensors is to gather streams of data, collate them, create structured records, and then make that data available for a range of applications, delivery over the cloud, and ultimately analysis. We are in the era, as I say here, of the connection of these different machines and sensors that are communicating together and performing functions almost in an autonomous way, the industrial internet, or the Internet of Things. Let's just give you a view of the Internet of Things for the sort of things that we might be interested in ourselves. We might have a series of embedded sensors which are perhaps focused on gathering particular environmental data, such as from sensors like these. A telemetric link is bringing that data back to our data center here. We might be bringing in real-time or near real-time satellite imagery coming through a base station. We might be working with unmanned aerial vehicles. Cranfield has a lot of experience working with UAVs for a range of different applications, and that data could be being captured. Of course, we can embed these sensors in vehicles as well, in trains, in cars and trucks, and of course in an agricultural context where we might be dragging sensors through the soil, looking at minute variations in soil properties as the sensor passes through. We might be bringing in transactions from financial world, legacy static data sets, and of course the range of social media, blogs, tweets, and so on, as I've mentioned. I'd like to give a case study, really, of big data in action, just to show you what you can do. This is a case study which is Network Rail, and I had the privilege of going on Network Rail's new measurement train as part of a project that myself and my students were doing, looking at flood risk management for Network Rail. They have a train which is called the NMT. It's covering 115,000 miles a year at a speed of about 125 miles an hour. This train is festooned with sensors. These sensors are collecting information on the track geometry, the spacing between the tracks, the ballast that goes around the track, and of course the overhead wire height and wear, signal strength for the cab driver, and a high-resolution video for looking at the forward. All of this data is being held, and it's being analysed against set tolerance levels, looking for deviations, for exceptions, and that is used to drive, of course, the maintenance upkeep of the scheduling and the track repair, sleeper replacement, and the vegetation management in the embankments. Pinpointing track fault locations like this makes an absolutely enormous difference over a traditional approach of sending engineers out onto the track. Just think about how much space you can run. I've got a couple of very short videos just to give you a feeling for how this works. The first video just shows you, I wanted to show you the infrastructure for storing this data even as the train is traveling.
What happens next is they start looking at how that's done by explain. What originally happened was they had a perfect image, sleep red, what perfect sleep should look like, what perfect rail should.
Look at those hard disks go! My goodness, extraordinary. However, even as the train is moving, as it's rushing along, the engineers are actually sitting on board doing the analysis. Just listen to what the head engineer is saying about it here.
Now, if you bear in mind, you can get that type of image going 125 miles an hour. It's pretty impressive. And they need to be able to do that, because not only are they finding where there is a fault, we also have to tell them when there isn't a fault. So it's important that they've got that ability.
Fantastic. It's really interesting what they're doing, making a big change to safety for all of us travelling on the railways. The next V is the variety of big data. So there's always been a challenge, if you like, in translating large volumes of data into decisions, transactional information into decisions. Just now that we're dealing with so many more types of information, we could think of variety of data in two ways. First of all, the variety of types of data, as I've mentioned a few times. Tabular, traditional rows and columns databases, but now as well all sorts of other types of data, hierarchical data, documents, PDFs, Word files, Excel, HTML pages, log files from web servers and so on, emails, real-time metering data, of course videos, image, audio, click trails from websites if we're doing marketing information, GPS tracking from our mobile phones, financial transactions and so on. It's very hard to actually structure some of these types of data using conventional relational database management techniques. We could also think of variety in terms of the sources of data. This data is coming from crowdsourced postings on the internet, blogs, tweets and so on. It's coming from web behavior that people are recording, mobile signals as we walk around, the digital footprint that we all leave, right, on Amazon or in the shops, embedded sensors as well in infrastructure and vehicles. Here's an example of what we're doing with variety of data. As we'll show you in the next room after this presentation, we're very fortunate at Cranfield to be responsible for the national soil map of England and Wales. And what we have is not just the map, but we have a lot of information about the properties of soil as well. And so we're interested in the contents of different types of clay that shrink and swell. And we combine this with climatological information from a variety of different sources and topographical information that tell us about the lie of the land. And then once we combine this with extreme events and with the location of infrastructure, houses, commercial, residential properties, shall we say the built environment, then we have a very powerful tool for exploring what the impact of the changing world is on our built environment. The way that we store data, of course, I think is changing as well. And I'll just in a few moments give a short summary here. The traditional model for dealing with, let's say, an organization with point of sales, dealing with transactional models of data, would have a series of transactional systems, cash registers and all the regional offices and so on, data coming down to an online transaction processing database, some sort of relational database probably, with structured rows, columns, tables, relationships of data. Simple reports can be drawn from this data, but of course what we're more likely to want to do is, as a business has more and more of this data, is not to actually start tinkering with the actual transactional data, but to make a copy of the transactional data to some parallel online analytical processing or OLAP database. And maybe data is copied on a batch basis, maybe at the end of a trading day or at the end of a week or a quarterly or whatever it is. It's not real time. And from this business intelligence, analytics can be run on the data cube that exists there, slicing and dicing data, drilling down and so on. Of course, if we're dealing with batch copies, a sophistication of that is to make that more real time, so that as a transaction comes in, our OLAP is being updated. The challenge in a sense is when we start to introduce big data systems into this, and I've kind of mentioned that because it's unstructured data, you can't really use the same database technologies to hold this. And there's a range of new hardware and software techniques which are emerging to deal with and handle big data. And that sort of unstructured data needs to find a place in the organizational structure for data. So those are the three V's of big data. I think I should say that actually Forrester, I believe, mentioned a fourth one, V. So of course, big data does provide value to organizations. And I think it's very important that organizations take this into account. Big data applications offer new insights. They allow us to predict and forecast the future based on experiences in the past, as long as we're very careful and cautious. You can assess risk based on a variety of data sets. You can conduct your business in new ways, increase the business velocity. You can look for new market segments. You obviously try to increase your revenue and cut your costs, and ultimately make better decisions. Just 6 quick examples of big data in action, really. First of all, road traffic forecasting. I'm sure we're all familiar with driving along, looking at our mobile phones or our not looking at them as we're driving, of course, but the TomTom or whatever that's giving us driving instructions, telling us about the road conditions up ahead. And in a sense, what's going on here is the mobile phone movements of hundreds or thousands of people on the road just ahead of us, as they're moving along, are being tracked, recorded, synthesized, combined perhaps with roadside sensor data, weather data, antecedent traffic from previous times to give us a forecast of road conditions. There's a lot of stuff on the internet at the moment about modeling the onset of diseases, mapping the spread of influenza, and models like this look at climate records, demographic data, tweets, of course, census information, aggregate medical records, and so on. Aircraft safety, engine monitoring. I've given this example. I know this is something that colleagues at Cranfield are strongly involved in, trying to actually look at exceptions from the norm as an indication that something may need to be maintained or replaced. And from a straight commercial point of view, market intelligence, social postings, tweets, purchaser history, market conditions. There's a lot of discussion about the notion of smart grids and smart cities, and I know, again, this is an area of great interest to a number of colleagues at Cranfield, looking at things like monitoring of traffic flows, managing energy demand, supply and demand. And this sort of information brings in census, and I know we have looked at CCTV and so on, and lots of data sets trying to look at the complexity of a modern cityscape. And lastly, just the environmental phenomena, as I've tried to indicate, things like flooding with Network Rail as I was working, landslips, erosion, subsidence, and of course heat waves affecting the population. So pretty much the last slide here, just to finish off by saying, who's afraid of the big bad data? Big data does come with a note of caution, of course. We are prosumers, as I started off by saying. It does come with a note of caution because we benefit from big data, of course, but we trade to benefit from it. We geotag our photographs. We leave digital footprint trails of our exploits and on the internet purchase using loyalty cards. Transaction details recorded, our medical records are being aggregated and made available, and we share our media with our friends and so on. So, of course, there are questions that do arise on a personal basis about cybersecurity, personal rights, privacy, and, of course, the jurisdiction even of where data might be stored out on the cloud. And these are issues where big data and law need to be discussed. In developing big data analytics, either for competitive advantage or to deliver socioeconomic benefits, of course, one of the challenges, and I think we'll come back to this in the next presentation, is choosing the right question to ask of your data. And of course, if you're working with data, it's got to be right. You have to understand the provenance and the accuracy of the data. So, there's the old saying about rubbish in and rubbish out. Uncertainty and visualization, and visualization technique